Hello everyone. Welcome to the classroom of Advanced Manufacturing Technologies for Welded Structures. Today we will learn the basic principles of bending and forming. And I am your lecturer, Joan Xingha. Bending and forming is a vital part of metalworking. Whether machinery manufacturing, automotive production, or aerospace, the bending process plays a key role. I hope that by today's lesson, everyone will gain a thorough understanding of bending and forming. First, let's look at the minimum bending radius of a bent part. The minimum bending radius refers to the inner radius on the bend. When a material is bent, its outer layer in the fillet zone undergoes tension, while the inner layer experiences compression with a fixed material thickness. A smaller inner radius induces more severe tension and compression if the tensile stress on the outer fillet exceeds the material's ultimate strength. Cracks or fractures will occur. Therefore, when designing the structure of bent components, avoid choosing an excessively small fillet radius. Next, let's examine the minimum bending radii for common metal materials. Different materials have different minimum bending radii, determined by their mechanical properties. For example, materials such as 08, 08F, and 10 have a minimum bending radius of 0.4 T, whereas 15, 20, and Q235 require 0.5 T. Be aware that high-strength materials usually demand larger minimum radii to prevent cracking or fracture during bending. Basic principles of bending sequence. After understanding minimum bending radii, we move on to the basic principles for bending sequence. A sensible bending order can improve production efficiency and product quality. There are three main principles: from inner to outer, from small to large, and from special shapes to general shapes. The inner to outer principle. Bend internal features first, then bend external features to avoid affecting the internal structure. The small to large principle. Bend smaller sections before larger sections to ensure precision and stability. The special to general principle. Bend unique or complex shapes first, then bend standard features to streamline production and maintain quality. These principles help prevent unnecessary issues during the bending process. Next, let's discuss the factors that influence bending quality. There are three primary aspects: material properties, die selection, and process parameters. Material characteristics such as tensile strength, yield strength, and elongation directly affect bending performance. High-strength alloys typically require greater bending force. Die geometry, dimensions, and material also impact bending accuracy and surface finish. Choosing the right die improves both precision and quality. Process parameters, including bending force, bending speed, and bend angle, must be adjusted appropriately for each application. Common problems and solutions in the bending process. 1. Bending fracture or cracking. In the bending process, one common issue is that the workpiece fractures or develops cracks. This usually occurs when the material's grain rolling direction is parallel to the bend line, which degrades its tensile strength and causes cracks or breaks at the fillet. Additionally, a small punch radius or a narrow lower die opening concentrates stress and can trigger cracks or fractures. To address this problem, adopt the following measures. 1. If the part's overall shape forces a rolling direction to be parallel to the bend line, increase the fillet radius from mild steel to at least twice the material's minimum bending radius. For high-strength plate, choose a punch radius greater than or equal to 4 times plate thickness. And within design limits, use as large a lower die opening as possible. 2. When the rolling direction is perpendicular to the bend line, the material's tensile strength is higher. So the fillet radius may equal the minimum bending radius. 3. Always ensure the plate's bending direction is either perpendicular or at a sufficient angle to its rolling direction. Never align bending with rolling. 2. Spring back. Another frequent issue is spring back. During bending, metal undergoes both plastic deformation and elastic deformation. Once bending ceases, elastic recovery produces spring back, which directly impacts dimensional accuracy and must be controlled. Different alloys exhibit different spring back angles. For example, low carbon steel can spring back between 0 degrees and 4 degrees under various conditions. To mitigate spring back, you can apply an angle compensation method. For example, if the workpiece's target bend angle is 90 degrees, set the V-shaped lower die opening to 78 degrees. Additionally, you can employ a dwell time compensation method. During bending, maintain pressure to extend the contact duration between the press brake punch, the workpiece, and the die. This increases plastic deformation in the die's fillet zone, so that opposing spring-back tendencies cancel each other out, thereby reducing overall spring back. 3. Slippage. Slippage is another common problem. 2 scenarios occur. One scenario is when the bend line and the workpiece's edge line are not parallel. The other is when the bend line and edge line are parallel, but neither end of the workpiece is supported on the press brake's lower V die. For these 2 scenarios, we can adopt different process measures accordingly. For the first scenario, the technician can add relief slits along the workpiece's bend line. Each slit's length should follow the outward offset of the bend line, and its width should equal half of selected lower die opening width. For the second scenario, the technician can increase the blank size on the cutting layout so that the workpiece edges rest on the press brake's lower die for support. After completing the bending operation, the excess material is trimmed with product drawing, and the slit edges are filed or ground to meet quality requirements. For indentations or scratches, during the bending process, the workpiece may also develop indentations or scratches. This is caused by the compressive force exerted by the upper punch and the lower die groove of the bending machine during forming. For carbon steel materials, we can increase the width of the lower die opening during bending. This enlarges the forming fillet radius and reduces the compressive force exerted by the die on the workpiece. In addition, non-marking, scratch-free dies can be fabricated to protect the surface of the workpiece and prevent indentations or scratches. The fabrication method for non-marking dies is illustrated in the accompanying diagram. 5. Forming interference and punch collision. Finally, let's examine the issues of forming interference and punch collision. As illustrated, let H represent the height of the bent workpiece, and let B represent its width. When H greater than or equal to B, the workpiece may be too tall and come into contact with the CNC press brake's back gauge or machine panel, resulting in interference. Conversely, if the workpiece is relatively small, its straight bend edge may collide with the upper punch, causing a punch collision. To resolve these issues, we can apply a reverse deformation bending method. First, create a blunt angle bend in the center of the workpiece. Then bend both sides, and finally repress the center section flat. For punch collision problems, replace the straight punch with a gooseneck offset punch to allow clearance during bending. Through today's lesson, we have gained an understanding of the minimum bending radius for bent parts, the fundamental principles of bending sequence, and the solutions to common problems encountered during the bending process. I hope you will apply this knowledge in practical operations to enhance both the quality and efficiency of bending techniques. Thank you all for your attention. That concludes today's lesson.